Hello physics and AP Physics. This is a quick introduction to some energy ideas that we're going to be using and how they relate to the work done as well. This will make more sense as we go and as you do some reading and in-class activities. But let's go ahead and start off for AP Physics. You'll be learning about work done by non-conserved forces. More on that in other content. And that work done by those non-conserved forces will equal the change in mechanical energy. For AP Physics and for regular physics, these equations are relevant. Okay? The mechanical energy of the system will be the kinetic energy plus the gravitational potential energy, and eventually for AP some other stuff. But for right now, we'll focus in on kinetic and potential energy initially. Okay? And kinetic energy will have to do with how fast the object's moving. So kinetic energy is 1/2 mv squared. So how fast the object's moving squared times its mass times 1/2, that'll give you its kinetic energy. Potential energy, more specifically this is gravitational potential energy, will be the mass of the object, and if we're near the surface of the Earth, multiplied by 9.8 meters per second squared, and then the height you are above whatever you call 0. And if you call the lowest point in your problem a height of 0, this will always be positive, and of course this will always be positive as well. So we're going to be doing with positive amounts. And one of the big ideas of energy is that for the universe, that when one type of energy goes down, some other type of energy goes up. And then there's this connection to work being done specifically for changes in certain types of energy, and for non-conserved forces, changes in mechanical energy for AP Physics. For regular physics, it'll be sufficient just to think about work done by stuff other than gravity causing this number to change. And we'll practice some stuff with that. Okay? But a lot of times, our mechanical energy of our system will stay the same. For AP Physics, that's when our work done by non-conserved forces is 0. If the left side of this is 0, the change in mechanical energy is 0. That's us saying it's not changing, therefore it's staying the same. And I have great confidence for certain setups where the mechanical energy of the system will stay the same. And now let's take a look at one of those setups. Let's see here. Is this going to be in the shot? All right, so here I have a bowling ball hanging from the ceiling, and I am going to do some work on this bowling ball by lifting it up. Okay, I applied a force upward. Okay, the displacement was upward. I did some positive work on this. I increased the mechanical energy of the bowling ball. Now what I'm going to do is, okay, I'm going to lift it up to my chin. Actually, no, not my chin this year. I'm going to lift it up to the tip of my mask, okay, and then I'm going to let go. And as long as I don't give this a push, okay, I don't want to exert any forces on this. As long as I don't give this a push, I'm very confident that the mechanical energy of this bowling ball will stay the same. We might have a switch from kinetic energy to potential energy and then back again. So like as it's falling down or swinging down, the KE will go up and the gravitational potential energy will go down, but the overall mechanical energy of the bowling ball will stay the same. And I'm willing to put my teeth, maybe not my life, but my teeth on the line for this, or in this case, my mask. Obviously, my mask is not going to stop a bowling ball, so my teeth as well. And I'm going to let go. So here we go. It's touching. 3, 2, 1. There we go. All right, I'll do it one more time. So right now, if I call this a height of 0, we've got a mechanical energy of the bowling ball of 0. Okay, that's my height of 0. I'm going to do some work on this by lifting it up. And when I do work on it, I'm exerting a force upward. It's being displaced upward, so that's positive work. That'll make the mechanical energy of the bowling ball increase. So we have an increased mechanical energy of the bowling ball when I lift it up here to my mask. Okay? And now I want to be very careful because I want the mechanical energy it has now to stay the same. So I don't want to give it a push. Otherwise, I'll be going to the doctor's office. All right, so I'm going to do it one more time. Very careful not to push, and then I'm not going to move. That's my intent anyway. It's tough not to flinch. 3, 2, 1. Ugh. All right. And in fact, the mechanical energy approximately stays the same. It actually decreases a little bit because if you noticed, it came up a little bit short of where I started at. The question is why? Why did the bowling ball come up a little bit short? All right, so there's two main things at play here that's doing work on our bowling ball or bowling ball rope system here, okay? And one of those things that's doing work, okay, that can change the mechanical energy of the system is air resistance. So as this thing flies through the air, okay, we're having to push air out of the way. Well, if the air is being shoved out of the way, okay, it's pushing back on the bowling ball because of Newton's third law, right? So that air resistance, that resistive force from the air, is opposite the direction of displacement. So when the bowling ball is going one way, air resistance is pushing on it the other way. So that does negative work and makes the mechanical energy of the bowling ball go down. So a decrease in ME. That's why it comes up a little bit short. And if I just left it swing back and forth, eventually it's going to come to a stop at the lowest point, and all of the mechanical energy will be gone. Now, it's not really gone. We'll learn about where it went later. The bigger idea is that if ME goes down, some other type of energy for the universe just has to go up. Okay? It is really as simple as that, and we'll get to that in one of our other units. Now, there's one other thing that you could have answered that would have been correct, and that is the friction up here with the ceiling or up above when I have it more open here. That friction at the pivot point, okay, that's also doing negative work. So if you think about it, when it's trying to move one way, friction will oppose that motion and it'll go the other way. So that's negative work, which will make the mechanical energy of the bowling ball again go down. Mechanical energy will go down. Quick review here as this is swinging back and forth. It has maximum kinetic energy right here at the bottom, the lowest point. It's all kinetic energy. At the highest points, it briefly, right there, comes to a stop. And when it comes to a stop right here, it's all potential energy at that point, and the kinetic energy is zero. So if you can picture some bar graphs, that would be great. As when we're here at the highest point, it's all PE. So we got a bar graph with all PE, no KE. As it swings down, it lowers its height, so potential energy goes down, and whatever potential energy goes down by, kinetic energy goes up by, because they have to add up to that same number if mechanical energy was staying the same. Now, we talked about it, it's actually going down a little bit, but we'll have an activity, a line writer activity, to get you to practice with those ideas. Okay? That friction and air resistance for AP Physics, those would be examples of non-conservative forces, and they're doing work on the system. For regular physics, you don't need all that terminology. For regular physics, all you really need to know is that if there's work being done by something other than gravity, your ME is going to change. Okay? And friction and air resistance aren't gravity, and they were doing work in the real world here. If we neglected friction and air resistance, then our ME would just stay the same. Okay? Sometimes people get concerned about the tension in the ropes acting on the bowling ball, if we're just doing the bowling ball as the system. The tension in the ropes will always be perpendicular to the displacement. So as it's swinging back and forth, it does this kind of, let me stop that, that's probably distracting. It does this kind of a thing, where that's the direction of the force. At any moment in time, that's the direction of the displacement. And as you will learn soon, or have already learned, to have work done by a force, the force and the displacement have to have a part that is parallel. Okay, they have to share part of the direction. So if they're perpendicular, there's no part of this force that's in the direction of the displacement, so there's no work being done. So there's a quick little crash course and a bunch of ideas. We will practice those with line writer activity, various questions and problems as well, and probably a couple openers somewhere down the line too. So if you have questions, shoot me an email or ask in class. This idea that we're using here, where I took it up to put my teeth on the line, okay? If instead I put my face down here, there is enough mechanical energy here in the bowling ball to take me out, okay? At that lowest point, if I'm right there and it hits me, that would be bad news. This is also the idea of a wrecking ball. So applications of this, just take a giant ball up in the air, let it swing down, put some stuff in the way, and you can destroy things. In non-COVID years, we could play, and we could do a modified version of this at home if you let me know in advance, okay? Or you could do it at home, okay? We would put some stuff here. You could bring stuff in for will it destroy. The idea of the wrecking ball, we'd put it there. And if it did destroy in the classroom, we'd go outside and I'd throw stuff off the hill down onto the concrete out in the front of the school to get it to destroy as well. But if you have items for will it destroy, we can set up, I just need to make sure it's safe. We can set up something that you can do at home if you want to do that for bonus. That is an option.